So hi, I'm Mathias. I'm part of the data science team of Azure Security Center, which I will present later. And today I will present an application of machine learning to security. So first, as you know, cloud security is an essential part of any cloud offering today. And Azure Security Center is Azure solution for this, where it's a centralized solution for cloud security monitoring. It's actually a tool that will help Azure tenants to monitor their subscription and security and give them tools to protect their environment, such as detection of advanced threat protection, but also recommendation and policy management. So as a cloud provider security service, we collect logs from various services, including, for instance, Windows security events, process creation events, login events, but also Linux machines, auditd, SQL logs. And based on this, we can define precise rules to look for specific malicious behaviors and then alert of them. For instance, if we see that Mimikatz is running on one of your VM, it's very simple. We are just going to see it in the process creation events. Of course, you need to allow Azure Security Center to collect data from your machines, and then we are going to give detection of, for instance, Mimikatz was run on your VM. So this is one example of simple detection that we are doing. Now let's talk about another scenario where attacks are not based on a single event, but on a series of simple events, let's say. So let's take an example where here we have a hacker that is breaching into a machine and then doing a series of steps. For instance, first he will detect the CPU of the machine, then detect the GPU, then do a task kill to kill the antivirus, then download a payload using a browser or any other wget, for instance. Then he will launch a task using Service Manager for persistency, and then he will finally run some app that is usually a Bitcoin miner, but it can be many different things. So, for instance, in this example, it's quite hard to detect that there is any malicious behavior on each single event, because each of these events, apart from the last one, is quite benign. So, but actually the sequence of events is actually a strong indicator of compromise. Okay, so how can we detect this kind of sequence of events? So first, we can also craft rules, but it will lead to overly complex rules. And also, because these rules are very complex, it will be also quite easy for attackers to avoid them by just altering some simple stuff, like changing a little bit one of the events in the sequence, renaming the files, for instance. And finally, it's very hard to maintain this kind of detections because you need to constantly update and adapt it to new threats. So this is why we are using a very different paradigm that is using AI techniques. So as you know, machine learning is a set of tools that let the computer learn how to distinguish by itself how to distinguish between a malicious behavior and a benign behavior from the data. It's able to learn from a set of samples and then generalize to new predictions. So it has many advantages. First, decision is based on complex patterns, which means that it's much harder for the attacker to avoid, because it's hard to understand what is the exact signal that is raising the alert. But most importantly, a machine learning model will be able to adapt automatically to new type of threats by simply retraining the model on a regular basis. So in Azure Security Center, we have been using this paradigm a lot with success for years already. And for instance, you can see my talk last year in BlueHat to see how we detect brute force using supervised machine learning. But we also do all kinds of steps. For instance, we give personalized recommendations for adaptive prevention based on user historical data, and you can see a blog post about it. So why does it work so well? One of the main reasons is that as a cloud provider, we have a really privileged position in this domain because we have a wide view of the attack surface. We have tons of customers being attacked every day, which gives us tons of data and the ability to understand in detail the attacks with the data collection that we have. And also we have a large security experience in Microsoft. So now how to apply this paradigm to our problem, which is to take logs and to make it as to make a detection out of it in security logs. So in order to do this, we thought of a similar problem, which is in a completely different domain. And we thought, okay, so logs are actually ordered sequence of events. And where do we see this kind of data? It's also in text, for instance. Text can be considered as an ordered sequence of words. And we have today a lot of research that is done on how to do sentiment analysis or how to get meaning of a text just by using the raw text, the text as a raw data. So what if it works also for logs? So for instance, we can consider a classification on a sequence of logs as a classification problem which is similar to a sentiment analysis problem on a document, on a text document, which is, for instance, you want to give you want to give a prediction of if a text has a good sentiment or a positive sentiment or a negative sentiment. So it's quite an active research topic today, and recent approaches have been showing very good results using neural networks and deep learning. So this is why we are going to use this today. So let's see how it applies to our problem. So first, we want to detect malicious IaaS VMs that are being compromised. And the first thing we are going to look at is strong labels of malicious and benign sessions to train the model and to train the classifier on. And for this, we look at login events that we have, and we say, okay, we have login events that happen to be from external IPs that are in TI. So these are considered as suspicious login events. And then if we take the full session that corresponds to this suspicious login, then we can already train it and consider it as a malicious sequence of processes. The problem is that even if so this is how we do. This is an example of how we can do to collect malicious labels of malicious sessions. And for benign communications, we filtered all the clients that appeared in any TI feed, and we kept only the clients that showed no anomalous behavior, no alerts, meaning that we removed any outlier. Sorry. The problem is that we saw that by using the TI thread as our input for malicious labels, we had some errors because TI is quite error prone. Indeed, there are a few caveats in TI, like an IP in TI can change owner very quickly. And we often lack the context to have a strong confidence in the TI, and that's why we use, instead of TI, we use honeypots. And because label quality is a very strong subject, actually a classifier is only as strong as its labels, where you train on. So as you know, IPs happen to be in TI when they do some malicious stuff. It doesn't mean that everything what they do is malicious. So for example, a VM can be in a botnet and be used to send spams, but it can also be used at the same time to do benign stuff. So if we take all the sessions from this specific VM, then we are going to have some malicious session and some benign session, and it will be hard to distinguish between each of them. On the other side, if we consider honeypots that are designed for catching a specific scenario, then it gives us very strong signals of malicious sessions. So this is why we use signals from honeypots from Azure VMs that have been attacked. So now let's look at the data itself and how we are going to apply the model on the data. So for each malicious login that we have, we look at the full process list in the process creation event that correspond to the same session ID. And we flag them as a malicious process list. And then we create a sentence for this login session, which is like the series of process names. So then we have malicious sentences and benign ones. And then we want to build a classifier that will be able to, if we give him a new process list, to tell if it's malicious or not. In order to do that, we need first to convert the data into data that can be parsed by the computers, by the machine learning model. And for this, we need to convert the data into vectors. So what we do is we simply vectorize the processes by using one-hot encoding, which means that we convert each unique process name into a unique vector of 1 and 0. In the end, we have, for each process, a vector of size, of vocabulary size, the vocabulary being the entire set of unique process names in the data. And because it's quite a large dimension, we do also a step of dimensionality reduction using Autoencoder's algorithm. So how it works? Basically, we want to reduce the dimension because we know that in machine learning context, models usually work much better on reduced dimension than on large dimensions. And we want to create a mapping where each process will be mapped to a vector so that processes that are usually seen together will be represented by vectors close to each other. And for this, we use the model called Autoencoder, which is well suited for this. Basically, the autoencoder is an unsupervised neural network that is classically used for word vectorization. And the method is that it learns to compress the data from the input layer into a short code, and then it does a reverse operation to uncompress that code and into something that closely matches the original data. And then if you use a code that was trained during the process, then it gives you a right estimate of a vector that actually encompass a meaningful vector about the process itself. So we have another problem, which is that let's say that an attacker would simply rename a process, a malicious process, to another name, let's say. So it will, and let's say that if the model is able to learn from a sequence of process names that it's malicious, what if the attacker will simply change one of the process into a different process name or generate a random name every attack? How are we going to deal with this? Because it will generate a new, different sequence of processes every time, and then the model won't be able to learn from it. So what we do is that we map each different rare process to the same ID. So each different, so it will basically consider each rare process to like if it was the same process. So now let me talk a bit about why we are using neural networks and not other type of machine learning models. Actually, we consider neural network in this problem because they are well suited for this type of data, which is raw data that hasn't been gone through a step of feature engineering. So usually in many contexts of machine learning pipelines, when you want to build a classifier, you are first going to build meaningful features, and this is something we wanted to avoid in this problem, so that the strong advantage is that the method here will be able to quickly adapt to any type of logs because it simply use the raw data. And also neural networks are well suited for this problem because even though they are quite expensive to train, they are usually using a lot of GPUs and computation to train the model. But after the model is trained, it's very fast to give predictions on new data, which means that for us it makes sense because we want to be able to give predictions in near real time on millions of machines. So now let's talk about the neural network itself. So a neural network is composed is composed of a series of layers and nodes that is called the architecture of the network. And each layer and each node is actually like a different function. So you can consider a neural network as a succession of as a sequence of linear functions and nonlinear functions, and the combination of these functions that are applied on the data actually make it able to learn very complex patterns in the data. So here we use an architecture that is usually used for sentiment analysis, because as we said earlier, this is the problem that we consider that it's most similar to our problem. And I will go a little bit into details about why the network works well for this specific problem. So the network that we're using is called convolutional neural networks because it actually includes convolution layers. And these layers, what they actually do is that they generate intermediate features on sliding windows of processes independently on their location, on their exact location in the sequence, which means that if the malicious sequence of events is happening at the beginning of the session or at the end of the session or in the middle of the session, it won't impact the results of the prediction, right? So this is why it's very strong in our context, because it gives us invariance by translation. So I will go a bit over like the few other steps into building the network. So very quickly, we are adding another layer, which is called the max pooling layer, that is actually used to obtain the maximum value of each different result of the convolutional layers. And then eventually, these features are passed to a fully connected layer that gives the final output, which is the probability of the sequence of being malicious. And we also add a dropout layer just before the fully connected layer for regularization purpose. So this is a very interesting, very important topic to talk about, because when you train a machine learning model, I forgot to mention it, but we actually split the data between a training set and a test set. And we want to make sure that when we train the data, it will be able to generalize well to new samples. And this is why we use techniques such as regularization to make sure that this has the correct behavior. So, given this architecture and given the training that we got actually pretty good results, as you see. Based on a recall of 96%, we were able to get a precision of 94%, which means that out of every prediction that we give, 94% are accurate. And if we compare it to other techniques that are classically used in this context of sequence of events, like naive Bayes or gradient boosting classifier, we see that it gives us very, very strong results. Which is not surprising, considering the fact that this is this is actually the state-of-the-art techniques that are used in the research. So a quick note about the infrastructure that we used. So we used Spark and CNTK and Keras. The Spark cluster, we use it to process the big data that we have, because we are collecting a lot events data on tens of and hundreds of thousands of machines, and we need a big data platform to process them and to transform these logs into matrices that are able to feed into the neural network. Then we use CNTK and Keras as our deep learning tools to train the model. And to implement it to the product, we use Data Lake and CNTK over C#. So after we validated this approach on the Windows security events, we wanted to also have an overview of how it performs on other type of logs. And this is why we also created a POC on Linux auditd logs. So we also did the same step of finding labels using honeypots. And we also trained, and also non-hacker script. And then we trained a model very quickly. And it was actually very, very nice to see that it was very, very straightforward to adapt the code that we did on Windows events to other kind of events like Linux auditd logs. It was actually very straightforward because it's exactly the same in architecture of neural networks and exactly the same model that we are doing, but just using different labels. And after training the model on these specific logs, we were able to find new detections, such as, for instance, the script that I'm mentioning here. So in this script, as you can see, it's a sequence of benign events like CD or make dir or very benign stuff that are happening, but the combination of all these signals, even if each signal taken separately is a very low signal or not suspicious at all, the whole chain of events gives us a very strong indication of malicious. So we saw that this attack, for instance, that would go under the radar with our actual single event detector was able to be detected using this approach. So as a takeout today, I would like to invite you to use more and more AI to exploit your logs. I think that this is techniques that are being used already in many domains and giving great results, and there is no reason why it wouldn't be used and helpful in security. So in order to do this, you will have to go through the process of collecting high-quality labels. And for this, I mentioned the honeypots that can give very strong labels, but you can also use feedbacks from customers. Also, you can use non-malicious scripts to train your models on, but also your security knowledge, which you can use to generate data. Thanks for your attention, and I would like to open it for questions.